Hey, everybody. Ah, the administrative matter. Is this better? Thank you. Okay. Thank you, thank you, thank you. Ugh. All right. For those of you who answered the Thanksgiving question, thank you. After 40 odd years in life, I just decided I don't like turkey, so we're having steak. We just went, yeah, love it or leave it, but that's, yeah, I know, right? I even make a good turkey, but my whole family was like, we just don't like turkey. So, and we like cows less than we like turkeys. Then Tuesday is going to be the quiz. If for those of you taking it at a time not in this classroom, there are alternate arrangements. The quiz will be offered Monday and Tuesday before class. There are some people who have exceptions to take it the Monday afterwards, but you've been in contact with Elaine, and I want to reemphasize what Elaine said on Campus Wire, that if you haven't reached out for accommodations by the end of class today, you need to be in here taking the quiz during class time. All right? Then when you come back, you're going to get the third problem set, which is super cool. It is. I was actually kind of excited about this one. So for the third problem set on Monday, you're going to take a happiness survey for us, which is just going to ask some basic demographic information of you, along the lines of like, what year are you? Roughly, I think I want to go back and we're going to talk about the questions, but it might include approximate GPA, 3.8 and up, 3.6, or wherever you are roughly. Whether you're a member of an eating club, like how many friends you have, how often you exercise, smoking, don't smoke, but like different things. And then we're gonna ask you a bunch of questions assessing your happiness on a 1 to 7 scale. And then what we're gonna do is construct a happiness index from the survey itself, and then just ask what are the major predictors of your happiness. Which I thought, I don't know, I'm kind of curious. I've done it a couple times before with this course, and like there's a couple results that just sort of are standard across the years, but we'll see how the group turns out. Just to give some background for that, the survey, and actually, we'll get to that in a second. The survey itself should take about 5 or 10 minutes, and if you don't do it, it's 10 points off your problem set. So do it. It doesn't take long. You'll look at it, it'll be very quick. And I want to put a plug in. I think I put this on Campus Wire earlier in the year. There was an article in the Princeton, and some people in this room were involved with it, that did a wide survey. Was it freshmen and sophomores, or was it the entire student body? Was that? Incoming first years, did it? Okay. But there was and I think I put it on Campus Wire, and if I didn't, it's part of this problem set, I'll just include a link to it. Take a look. Some of the questions overlap, some don't. And they were doing a lot of summary statistics. It was genuinely interesting to see where people fell. We're not going to be doing summary statistics as much as regression analysis, but the idea is kind of the same. All right, so any questions on that before we roll ahead? Cool. All right. Then let us proceed without further ado. Okay. The first idea we're going to discuss today this is a type of variable called fixed effects. And it's a type of covariate. A fixed effect is a variable that takes on a value of 1 if you're in some level and 0 if you're not. And here's the formal definition is that a fixed effect is a mutually exclusive and exhaustive set of indicator variables. Let me give an example. Let's say we're to ask everyone in this room what country you were born in, okay? And I wanted to include information on that categorical variable in a regression. What would happen is I'd gather that as a factor, and then R would interpret that factor as a series of 0, 1 variables for every level of the factor. So some people presumably were born in the United States. So there'd be a variable that said factor _ United States. And it's a 1 if you were born in the United States, a 0 if you weren't. if someone in the room was born in Switzerland. Then there'd be another variable that said factor underscore Switzerland, 1 for if you are, 0 if you're not. And it turns a factor, which is just an unordered categorical variable, into a set of 0 ones, so that everyone falls into one category. Fixed effects are a useful tool in applied regression analysis and used quite commonly to adjust in a regression for something about a particular group. So let's say we did the happiness survey and we put in the question, what country were you born in, right? If we include that in the regression, then there'd be a variable that would be, here's the average, everything else equal, here's the average for people who are born in the US. Here's the average for people who were born in Colombia. Here's, and it would allow us to model specific groups in our data using these indicator variables. There's a few different ways to go with fixed effects, and we'll talk about a few different uses over today's lecture. But the idea behind it is it's a way of translating a categorical variable into a set of 0, 1 variables that R can understand. We'll talk about how to use them and why to use them, and then about the interpretation. So in this case, we're going to look at national election study, the American National Election Study data. It's out of Michigan. It dates back to the late 50s, but it really kicked in the 1960s. It's the longest running ongoing academic survey that's directly comparable back to roughly Kennedy's term. So what you'll encounter in that data is a variable for party ID. I believe you've used this in one of your handouts. And in this case, the party ID is done on a Likert scale. And a Likert scale is just an ordered variable ranging from least to most likely, from lowest to highest on some variable we care about. The Likert scale for partisanship in the ANES runs from strong Republican to moderate Republican to weak Republican, independent, weak Democrat, moderate Democrat, strong Democrat, right? So this is an ordinal measure, by which I mean independents are not 4 times as liberal as strong Republicans. There's nothing about the magnitude of that, right? It's not a measure where 2 is twice 1. It's simply 2 is more than 1, 3 is further along, 4 is further along. So Likert scales are commonly used in surveys. Another example where you'll see fixed effects show up is by year. This shows up quite a bit in academic studies. And in this case, when might we want to control for year? You're running a regression that has data from multiple years in it, and you just want to control for which year you're conducting, for which you want to control for year-to-year peculiarities. And that's what the fixed effect is going to do. It's going to say, if something odd was happening in 1996, the fixed effect will pick it up. If something odd was happening in 2000, the fixed effect will pick it up. So let me show you how this is constructed. The variable right there is year. And in that case, if the observed year is 1996, then there's a variable 1996 that takes on a 1 if the observation that you're looking at was recorded in 1996 and a 0 otherwise. The next observation, observation 2, is 2008. So that's going to get a 0 for 1996, a 0 for 2000, a 0 for 2004, and a 1 for 2008. Similarly, 2004, the third observation, is going to get a 0 for 1996, a 0 for 2000, a 1 for 2004, and a 0 for 2008. The final one, which is 1996 again, is going to have a 1 in the 1996 column, and then a 0 afterwards. So what we're doing is we're taking this categorical variable and we're breaking it up into a string of zeros and into a set of 0s and 1s. By mutually exclusive, if you look at how they're broken up, it means that every observation falls into exactly 1 level. And by exhaustive, it means that every observation falls into some level. So in that case, if you add up across the rows, they add up to 1. They're mutually exclusive because every observation has 1, 1, and the rest zeros. And it's exhaustive because it has exactly 1, 1 in the row. So there's one trick to interpreting fixed effects that we're going to have to talk about. And that's the idea of the baseline category. If you take the fixed effects representation of the year variable that's up there, and you add up across rows, you're going to get a 1 all the way down. For those who have taken some linear algebra, that just means that that matrix is rank deficient. In other ways, saying that the columns are linearly dependent. They all add up to 1. This creates problems in R. And let me tell you how it will deal with it. R will drop the first level, and the first level of a fixed effect becomes what's called the baseline category. And everything gets interpreted relative to the baseline. So let me give you an example of how to read these things in the next slide. Oh, this is the party ID variable, the Likert scale broken up into fixed effects. So in this case, strong to weak, strong Democrat to strong Republican. You'll notice that a 4 goes there, a 2 goes there, a 1 goes there. So here we're taking this variable for party ID and breaking it up into fixed effects. This representation and the one with year reminds me, one note I want to make. When you're running this in a regression, you need to tell R that party ID is a factor if you want it to show up as fixed effects. Otherwise, it'll include it as numeric, which is a lie. And we've hit that conversation a few times in this course. But let's take a look at this. This is actually from the last time, about 4 years ago, when I did the happiness survey study that you're going to do for your third problem set. And the first part of this, we're going to look at the left-hand side and the right-hand side. At the time, and we'll give you some better instructions for this one, but at the time, the output went from R to Excel into a Word document. And that's kind of, we were asking you to format the results. So if you look at the left-hand side, that looks pretty close to what R gives you, right? The point estimate is up top. Right below it is the standard error. Does anyone know why the standard errors all have negatives in front of them? Standard errors have to be bigger than 0. R returns the output in parentheses, and that's an accounting convention for making a negative number. So it interpreted all the standard errors as negative, which is confusing. You just have to kind of like be aware of these things. The first point I want to make is to go from the original output on the left of your regression to the output that you'd handed on the right. The first thing to do for my course, but also for JP senior theses, professional work, academic work, what have you, is you rewrite the variable names. Including raw variable names in output that you're handing in as a final report is just insulting to the reader. Okay, it's like misspelling your title or something. It's just tacky. It's just a sign that it's not put together well. So if you're ever handing in something as a report for me, I'm going to want to see it, or just for your JP or senior thesis especially, you don't include raw variable names, you just rewrite them. So in the equation, let's take a look and analyze the one on the figure on the right, which I hope you all agree looks cleaner, right? More interpretable. Before you hand in a regression table or even a figure, spot check it, even have like your roommate or someone take a quick look at it and make sure it looks okay. It often only takes a split second to tell if something is awry. So in this case, the outcome on the right-hand side for model 1, one thing to note as well is we went from 5.0353 to 5.04. Including 6 or 8 significant digits in a social science study is considered pedantic. Just don't, right? Like this ain't physics. 10th place is good, 100th place is good. We don't measure things to like the quantum level here. All right, everything is just noisy. So on the right-hand side, This is a regression where for that particular year, the students were asked to regress the happiness index that was created onto a bunch of fixed effects. Okay, what fixed effects are there? Well, there was a fixed effect for self-identified gender. There was a fixed effect for how frequently do you exercise. There was a fixed effect for how many friends do you have, and all of these are questions that were asked. All right. So we're going to talk about how to interpret these things. Before we head into the interpretation, one interesting ethical issue comes out of here, which is anonymizing the data. Because I really, in this particular year, there were 2 students that didn't identify as male or female, and they were in 2 separate years, which meant they were actually de-anonymized by the survey, right? Because you could look at because you all had the data, you can go back and learn the information about the people who answered those questions, which then created the thorny issue of, well, do we do a level of self-identified male or not, or self-identified female or not? And all of these sorts of things come into play when you put these surveys together. So we're going to need a little time with your data before we give it to you to de-anonymize it and make sure everything's formatted. But like even in simple studies like this, issues come into play, especially if they're sensitive information. And some of the questions, they're not wildly sensitive, but I wouldn't want to broadcast to everybody, right? I don't know the makeup of this group because it's post-COVID, but normally there's a lot of sophomores in here. And some years there were only 3 freshmen. So I just had to have sophomore or before, or junior or not, junior or later, so that you couldn't pick out individual people. And we stopped asking about what college you were in, because that really de-anonymizes people once you get like the right covariate breakdown. De-anonymized data is not good. If your data can be de-anonymized, don't send COVID information out to the entire university. I just have to, like, while we're on that, and it seemed an honest mistake. These things happen. It didn't seem malicious in any way. Just check who's in your BCC. One other comment about the de-anonymizing data. Does anyone remember the Netflix prize? Okay. Before you could stream on Netflix, do people remember DVDs? Yeah, no, I don't, I mean, like, okay, you knew they were a thing. They're like the internet, but like in disc form, and then you could like put it in and it plays. Netflix used to work on a subscription model where you could get up to 3 DVDs at a time for like $8 a month or something. And then you'd mail them back and get it back in 2 or 3 days. When you were using Netflix in that form, it was actually really expensive to try a new film. So their recommender system was really important, right? Like I can go on to Netflix now and watch, oh my God, 5 minutes in, I was in love with the Tiger King. Season 2 is coming out. If I disappear to South Carolina and start a tiger farm, you know why. I've briefed my wife on this. She's not quite on board, but we're still having that conversation. But like, if you don't like something, you can flip it off, right? With DVDs, that wasn't the case. So its recommender system was really important because it was a 3-day lag between you deciding and then like you forget to put in the mail and like that sort of thing. So what Netflix did was it created a competition called the Netflix Prize, where they gave a whole bunch of data off how people rated things. And then it held some data back that no one ever saw. And what you had to do was give a model that would predict, given what people liked, the number of stars that they'd give to other new movies. And then once every year, I believe it was, they'd give a couple $1 million to whoever had the best prediction on the data that you never saw. Folks see that? It was kind of cool. It actually created a small literature on the Napoleon Dynamite problem. Has anyone seen Napoleon Dynamite? Can I see hands who's seen it? Okay, who thought it was absolutely awesome? Leave your hands up. Who thought it was absolutely horrible? Leave your hands up. Okay, it turns out, Jacob, sorry, um, that observationally equivalent people split on whether that is the most amazing movie ever, which, sorry, Jacob, it is, or whether it is just utterly wretched. And it turned out that like a lot of the results, like real money based on who won the competition, was based on your ability to predict whether people would like Napoleon Dynamite. And it was just a coin flip. And I hope people who have seen the movie can appreciate the aesthetic behind it. That, yeah. So at some point, some clever person took the Netflix data and de-anonymized it. And then there were like 20,000 people or 80,000 people or something like that. But there were a large number of Netflix customers whose viewing history and their preferences were released to the public. Netflix shut down the competition shortly thereafter, in part because of the de-anonymization, and in part because they were switching from the mailing to the streaming. Right? You know, it's the ratings are less important when you're streaming. Okay, so de-anonymizing data, be aware, especially when you're doing work, and I've been involved with a few senior theses and a few projects of my own, and a few projects with grad students where de-anonymization is genuinely important. As throughout this course, we've been using publicly available data, and quite frequently you'll be asked to make your data publicly available. So realize that people should not be able to go from what you're analyzing to individuals. Okay? Okay. All that from self-identified gender and course and what year you are. Okay, so let's talk about how to interpret this. The intercept is giving us the happiness measure if all the other variables were 0. That's just the quickest way to think about it. That's kind of a weird, well, could that be the case? Yes. It's characterizing a non-self-identified male with, well, we'll talk about that. But let's look at the male category, okay? What that fixed effect is saying is that relative to the excluded category, which is non-self-identified males, self-identified males are 0.17 points higher on the scale. Does that make sense? It's not saying that males have a score of 0.17. On a 1 to 10 scale, that's just not the case. It's saying that relative to the omitted category of non-self-identified males, self-identified males are 0.17 higher. Is the effect statistically significant? No. Why? There's no asterisk, but also the point estimate is about half a standard error. So you can look at it and eyeball the t statistic, which is 0.17 over 0.31. That's not larger than 2. If anything, that's 0.6 or so. The important new point is that the measure in self-identified males is relative to the baseline of non-self-identified males. Now what we're going to do is look at another question that was asked and analyze those results. So we ask, how many times a week do you exercise? Right? 3 to 4, greater than 5, no exercise. Okay. When you look at that fixed effect, the first question you have to ask yourself is, what's the omitted category? Because everything will be interpreted relative to the omitted category. And this is the result of, this results from all the fixed effects adding up to 1. We have to take 1 column out in order to identify these coefficients from our data. Does anyone see the omitted category for exercise? Yeah. Yep, exercise 1 to 2. It's called the omitted category because it ain't there. R dropped exercise comma 1 to 2. So all of the coefficients are interpreted relative to the baseline of exercising once or twice a week. This is telling us, if we look at exercise 3 to 4, people who exercise 3 to 4 times a week are 0.04%, have a higher score, a 0.04 higher measure of happiness. But the standard error on that is 0.37, so that's not statistically significant or substantively on this scale. So people who exercise 3 to 4 weeks are statistically indistinguishable from people who exercise once or twice in this survey. Right? Let's go ahead and look at exercise greater than 5 times a week. Oh my God, they're not happy. Okay, but it's not significant. So exercising greater than 5 times a week, you have a score, you score about 0.71 points lower relative to people who exercise once or twice a week. And the important part is the relative to once or twice a week. Okay? So that's 0.71 points lower. The standard error is 0.46, so it's not a statistically significant difference. Who is unhappy? People who don't exercise. Yeah.
Well, if you want to compare to people who exercise.
I'll get to the mechanics of that in a moment. Okay? The question was, is this an interesting baseline? Right? Let me get to that in a second. The no exercise, well, if you don't exercise, then your happiness score is about 0.76, lower than 1 to 2 times, and the effect is statistically significant. Why is it? Because the 0.76 coefficient is more than 2 standard errors below 0. So it's not, so that coefficient isn't telling us that people who don't exercise are unhappy. It's telling us that people who don't exercise are statistically significantly less happy than people who exercise once or twice a week. Okay, you know my is it causal question coming. I'm just going to leave that to you. But that's the prediction we have. Now the question is why once or twice a week, right? The answer is R drops the first one. So the variables were coded 1 or 2, 3 or 4, 5 or 6. Sorry, 3 or 4, 5 or greater, and then none. N-O-N-E, so it puts it at the bottom. So it dropped 1 or 2. There's a command. I guess we'll just give you the command in the problem set called recode, which lets you change the levels to choose a baseline. You might be more interested in taking exercise not at all as a baseline, right? And just seeing what's the effect of going up from there. Does that make sense? So as a researcher, sometimes fixed effects aren't interesting. You just want to control for a year. Sometimes they are interesting. If they're not interesting, it doesn't matter what your baseline is. You get the exact same answer for your other coefficients. If it is something you care about, then you have to designate a baseline that's meaningful to the reader. In this case, you could look at it and see that exercise 1 to 2 was the omitted category. But there are times where like you're using fixed effects for religion, and it's not at all obvious what the omitted category is. Okay? So if you need to choose a meaningful omitted category if you're analyzing that particular relationship in the data, and if it's not obvious what the omitted category is, just put it at the bottom of the table. Omitted category is blank. You see this regularly in regression tables. Going to the next, let's look at the next fixed effect. This one puzzled me, by the way. Anyone want to take a stab at what the friends fixed effects are telling us? First, what's the omitted category? No friends, so we're talking about the friendless. But friendless people seem to be scoring happier on the index. Do people see that? Okay, so I do recall announcing to that group, we'll see how it works out in here, but start shedding friends. I'm kidding. I just need to say that because in case someone realizes at this time of the semester that like 2/3 of the things I say like that are jokes. I'm actually kidding. Okay, so this is saying that reporting no friends actually gives you a higher score on our happiness index by 2.5 percentage points with a standard error of 0.98. Now, mind you, this is on a 1 to 7 scale. No, it's on a 1 to 10 scale, sorry. This is on a 1 to 10 scale. So 2.5 percentage points that's solid. That's substantively significant. So people who are friendless seem to be more content with their life. Okay. I follow the data. Then whether having 3 to 5 friends is actually kind of the same. Having 1 to 2 friends are relatively unhappy, but the 3 to 5 friend category and the greater than 5 category, there's no statistically significant difference between having no friends, 3 to 5 friends, or more than 5 friends. But people who have 1 to 2 friends are just seem to be less happy. Does that match up with anyone's in that one? I still scratch my head at. Does that match anyone's intuition? What's that? Some people like being alone. Yeah. That's a different question. I'll leave. We'll see how that one turns out. This class is great for relationship advice, by the way. Okay. Onto a different question. We're going to talk about what fixed effects and indicator variables can do in a regression. At this point, we're foreshadowing a large class of models called hierarchical linear models, which are ubiquitous in sociology, common in political science and economics. You will see them. So I want to give the basic intuition of some of these ideas in a very simple setting. All right. And what we're going to do is we're going to think of a fixed effect as adding an intercept for a different group. So it's allowing the intercept to change from group to group. We're going to go back to the democracy and Islam data. And we're going to assume the following model. The outcome is beta 0 plus beta 1 times whether the observation is in the Mideast, plus a slope term on Muslim participation in the workforce. That's what the Z-Islam was. It was scaled to a Z-scale. We've seen this data a few times. The important point I want to give to you now is what happens when we put a fixed effect like Mideast into a regression, what's it doing? And the point is that it's not touching that slope term, it's only lifting the line up or down. So let me show you, this is called a differing intercept model, sometimes also called fixed effects by region. And that's well, here, we're going to take these slightly out of order. This is the result for the differing intercepts model, sometimes also called putting in fixed effects by region. So in this case, we just have 2 regions, Mideast and non-Mideast. And what you'll notice is that with the lines that we fit, we have the same slope for the Mideast and non-Mideast countries, but the intercept shifts. So we're saying there's some level shift in the model we're fitting between Mideast countries and non-Mideast countries, but the relationship between proportion Muslim and the outcome female labor force participation is the slope is held constant. This differs from a differing intercept and slope model. And that's the model that's here. So here we have an intercept. Then we also have an indicator variable for whether you're in the Mideast or not. That's going to give us a different intercept. But then we have the slope variable on the relationship between proportion Muslim and female labor force participation. Then we have another variable, which is Mideast times Islam. So what that's going to do is when Mideast is 1, it's going to change the slope on Islam, the relationship between proportion Muslim and female labor force participation. And what this will allow us to do is model the 2 groups, not just with a mean shift, but also a slope shift. So what we're doing in the previous model, we were giving Mideast countries and non-Mideast countries their own slope, but giving them their own intercept, but restricting the slope to be the same. In this model, we're giving them separate intercepts and separate slopes. So to show you what that's going to look like in the data, that's going to give us a figure that looks like this. So this is the same slope, different intercepts model. This is the different slopes and intercepts model. Which model do you choose? We'll talk about that a little bit more next week, because it's much more art than science, to be completely honest. It's a set of aesthetics that vary from field to field. The point that I want you to see now is that by putting in a fixed effect, you're changing the intercept for each region, but keeping the slope on the variable you care about the same. You can also create an interaction between the intercept and the slope that you're looking at to allow the slope to change from group to group. And the amount of flexibility you fit to your model depends in part on your question and how much data you have and how much the data can support. We will get through as much of this as we can. In order to do it in R, here's some code for it. But for the last few minutes, we're going to talk about difference in difference estimation and cocaine. No, I'm serious, this study. So in the early 90s, through the 1980s and until about 1992 or 1993, most refined cocaine in the United States came from Colombia. And quite a bit of it actually came because apparently you grow the coca leaves, then you dehydrate them. And that's where most of the mass goes away in that dehydration step. And it turns into what's called coca paste. Then the coca paste is actually brought to refineries, normally in Colombia, where they're refined through some chemical processes into cocaine that are shipped up to the United States. And that apparently is the normal traffic. That's the way that cocaine gets from there to here. So in the early 90s, the United States started shooting down airplanes over what was called the air bridge, which were planes flying in from Bolivia and Peru into Colombia with coca paste. It was part of the war on drugs, which for those of you who study these things has been wildly successful. That was also me kidding. It has not. So the planes are getting shot down, bringing the coca paste in from Bolivia and Peru. This started in 1993, 1994. In 1993, Peru actually had an autogolpe, a self-coup, where there was the president just basically maintained power. And the politics of Peru, in part as maintaining power, was actually shutting down the production of the production of coca leaves, the growth of coca leaves in Peru itself. So what happened was that the urban areas of Colombia that were refining this coca paste were unable to get it from Peru or Bolivia, but the demand did not dissipate. So large amounts of coca leaves started to be grown in rural Colombia, where it wasn't before, because you didn't need to fly it in. You could just drive in the coca paste, all right? All of this was done in an exogenous shock circa 1993, 1994. The idea behind this is that all the immediate money that was brought into these rural areas was something of an economic windfall. These were areas that were making a lot more money because of effectively a tariff, right? Shooting down the planes it's a harsh tariff, but it's a type of tariff that was being imposed on Peru and Bolivia. And so the rural areas started growing more coca leaves, and it led to a massive influx of money into these regions. This raises the question of whether this massive influx of money was good for the area. For folks who study these things in comparative politics, there's an entire literature on what's called the resource curse. The problem in this paper is compared to diamonds or precious metals in Africa, where you find these highly precious commodities. Does it help the politics? Does it help the region? What's the impact on the region of having this influx due to a sharp increase in demand and just a lot of money coming in? So this is a difference in difference design, where what the authors can do is compare different results before and after in Colombia to before and after in these other countries. the result that we're going to look at is log of violent deaths +1 over log of population +1. All right, this was the outcome that was used in the original study. The results are logged. Those numbers are logged because they're highly skewed. We've talked about this a few times, but logging population in these sorts of events is common. And the +1 is because there are some zeros in there. So by adding 1, it stops you from working with log of 0, which is technically negative infinity, but we're not going to, it allows R to not drop that observation from the data. The authors didn't even justify this decision in the paper. It was just par for the course with this. The observations can be demographic group by region. In Colombia, looking at areas that had huge explosive growth in coca versus not. Then, before is going to be 1991 to 1992. In stating the air bridge was not immediate, nor was the self-coup in Peru. So we're going to call the after period 1996 to 1997. So between 1992 and 1996, what we're saying is that that's when the disruption occurred. And that's enough time for all the equilibrium effects to have settled in. The treatment variable is whether coca was grown in the region. And then there are additional controls in the model for age, sex, dummy variables per region, and population. So the question we're asking here is, did this huge influx of money and economic growth lead to more violent deaths? So let's look at the results and see how we get it. This is some R code that gives us the results from the study. And this is how we've been doing difference in difference estimates. If you can read it, after and growth regions minus before and growth regions, and after and non-growth regions minus before non-growth regions. Do folks see the two differences up there? And then we do the difference in those and we get 0.197. That's cool and all. We've been doing that since week 1 or 2. The question is, how do we do this and start doing inference on this? How do we get a standard error on it? How do we show that it's statistically significant or not? The answer is an interaction term. So what we're going to do is we're going to fit the following regression. We're going to regress the outcome, which was the log of deaths +1 over log of population +1. We're going to regress it on a dummy variable for before or after, a dummy variable for treatment times treatment or not, and then the interaction between the two. And by the interaction, I literally mean the element-wise multiplication. So in this case, we create a new variable called grow after, which is grow, which is a 1 if they grow coca in the region, 0 otherwise, times after, which is a 1 if the observation is after the air bridge disruption, or a 0 before. And that's going to pull out, that's going to assign a value of 1 to all the observations that are in growth regions that are growing coca and observed after the disruption. And we're going to include in our regression grow, which is our treatment variable, after, which is our time variable, then grow times after. Now, what do we get when we do this? I want you to recall that our estimate was 0.197. If we run this regression, we get exactly the same point estimate. It is numerically the same value. Recall how we could use a regression to get a difference in means estimate with a dummy variable? This particular formulation will allow you to use an interaction variable to recover exactly the difference in difference estimate. Okay, so it's completely analogous to putting in a dummy variable, a 0, 1, to get a difference in means. Creating this variable in this setup will give us exactly the difference in difference estimate. Okay, great, so we can calculate difference in difference estimates multiple ways now. Yay, why? 2 reasons. The first reason we do this is because now we have a standard error on it. So we can construct a confidence interval and look at p-values. So looking at it, was the effect statistically significant? Was the difference in difference estimates statistically significant? Yes or no? Yep. Okay. Why? Because the estimate's 0.197, its standard error was 0.082882. You can stop there and multiply 0.0882 in your head and say, oh, that's about 0.167 or something, or 0.176, which is less than the 0.197. So it's more than 2 standard errors away. If you want to continue down the table, R does that for you and says, well, it's actually 2.23 standard errors from 0, which is statistically significant. In case you're not completely convinced, it actually gives you a p-value. In this case, 0.0255. All right. So the first reason we do difference in difference in this framework is it allows us to conduct inference. I can ask you what the confidence interval is, what the p-value, is it significant, all those things. The second reason we do this is we can actually include covariates if we want. So whenever you run a difference in difference, you need to include this baseline model with no covariates. And then you can also adjust for age and education and population of the different data that you're looking at. Technically, it shouldn't make a difference, but sometimes it does, and reviewers are always comfortable seeing that your results hold across 2 or 3 or 4 specifications, that it wasn't just one specification that gave you the answer. So in this case, we can include additional control variables into it in order to get better results. So this is one example of what these results can look like. With a difference in difference design, always include just the treatment variable, the time variable, and their interactions, the first model. And that's 0.197. Then what you do is you include 2 or 3 or 4 other models. We just put 2 other models in here so that the reader can see that the results aren't driven by a particular model. No matter how you control the control variable, include the control variables, you get roughly the same result. So the thing to see here is that in the second model, we add age and gender. Then in the third one, we add population. We'll talk about why that's a 0 later, time permitting. But across the 3 models, that grow after coefficient is significant across all 3 specifications, which is what you want to convey to the reader. No matter how you include your controls, you get approximately the same result. I will see you all on Tuesday.